You probably know that situation of being in a conversation about going somewhere by car or by plane, and someone, maybe you, mentioning that the odds of getting killed in a car crash are way higher than in an airplane crash. That doesn't mean it will make everyone feel really safe, but it is true. Now, the probability of dying from a car crash depends on two things: the probability of being in such a crash when being in a car, times the probability of dying when in a crash. So what you see is that transport organizations, manufacturers, governments, they tend to do two things for safety. First, they make accidents less likely by building safer roads, having traffic regulations, and requiring training, a driver's license, for the operation of these devices. Next to that, they make the device safer, so the chance of dying, if you are in a crash, becomes lower. Think of seat belts, airbags, and all kinds of driving assistance technology.
For risk control of medical devices, we have these three types of measures. First, inherent safety of the device and manufacturer. This is the preferred way to go because inherent characteristics of the device are more likely to stay effective than an alarm or warning. With an inherently safe design, you could eliminate a hazard entirely, reduce the probability of the hazard leading to a harm, or reduce the severity of a harm. For example, by improving the safety of your device running on high voltage electrical mains power, not by just putting a warning label on it, but by changing its electronics to run on low voltage batteries instead of mains power. The second type of measure is by adding protective measures in the device itself or in the manufacturing process. These are things like alarms, safety valves, and protective elements in your design or visual inspection of the device during manufacturing. Such measures do not necessarily prevent the hazardous situation from occurring,
Mind your table.
but they
Mind
can
your
block the
table.
chain of
Mind your
events
table.
before it leads
Mind
to
your
harm.
table.
A third type of risk control measure consists of providing information for safety to anyone relevant in the manufacturing and use of the device. Think of providing manuals, putting warning labels on the device, and training the people making or using the device. This is the least reliable, but sometimes only way to reduce the risks to an acceptable level. Least reliable because training can be forgotten or put aside in certain situations, warning labels can be ignored or removed, and manuals, well, when did you last read one properly?
Sometimes warning is all you can do, like with a scalpel. You can warn users that it is sharp and train them, or even assume that all adults know how a knife works, but you can't make it blunt. With information for safety, you can, if the users follow the instructions, avoid hazards with signs of what not to use a device for, avoid use errors with a clean instruction manual, or reduce the severity of a harm by teaching the user what to do if something goes wrong. A risk control measure can work by eliminating or reducing the probability of a harm occurring, by reducing the harm's severity, or both. When implementing risk control measures, it is important to keep updating your risk management file because the solution for one risk may affect other factors or introduce new risks. Therefore, you must verify the implementation and effectiveness of the risk control measures that you put in place, because that you think something will help reduce risks doesn't always mean it really does. Now let's take a look at the risks we want to control for our electrosurgical system. Some of these issues are part of a joint problem, so we tackle these together. We will explain why in a minute, so just hang on. And then we reorder everything so the risks that are suitable for an inherently safe approach are on top, and the risks we will try to control via information for safety are at the bottom. The top set of risks arises from a serious flaw in terms of usability design. In several ways, the pedals, the connectors, and in- and output ports are currently designed such that users can hardly distinguish one from another. You could explain in the manual that the left pedal is for cutting and the right port on the generator is for coagulation, But this is something that users will easily forget, or can be confusing because left and right depend on your viewpoint. Furthermore, in dimly lit environments or emergency situations, the interface is not intuitive enough to let people automatically plug into the right port. Now, we could solve all that by making the device more inherently safe. This is how such a solution could look like. On the generator, there are two separate screens for the settings of the cut and coagulate modes, and they have different color frames plus a large label saying what they are for. The three connectors have each been given a unique connector shape, so one can never connect the handheld device to the foot switch port or vice versa. The foot switch pedals now have corresponding colors, so we always know which one does what. On top of that, the foot switch is now designed such that you can only use it from one side, so the yellow cut pedal is always on the left for the user, even without the user choosing to do so. Some of you probably already know, but if you browse around for similar medical devices, you will see that many were designed with the same approach. And that is partly because some of such solutions are even prescribed in ISO standards for specific groups of devices. Now, the issues with improper adhesion of the return electrode could maybe be improved a bit by using better sticking and conducting glue, but that will make removal of the patch bad for the skin. If the adhesive layer would be made to conduct extremely well, the patch will also work with a small contact area. But then the current density will become too high and cause skin burns. So for the new design, we will not prevent the hazardous situation of an incompletely adhered return electrode occurring, but if it occurs, we will let the screen of the activated mode blink and show a descriptive error message. And we will trigger a loud enough alarm. That way, the user will be made aware and they can adapt their surgical approach. Another issue to be solved with protective measures, but of a very different kind, is a production flaw in the scissors connection port. Production flaws just happen now and then. It is unlikely that we will be able to prevent the connector production to ever be flawed. Machines and materials may fail, production workers make mistakes, it simply happens. But we can prevent these mistakes from leading to a faulty product being used by interrupting that chain of events at a convenient point in the process. We could do that by introducing visual inspection between the moment the product is finished and the product has been packed and shipped. That way, faulty connectors may still be made now and then, but they will not end up in a device that actually reaches the clinic. And the last risk that we will tackle for now is the situation of accidentally having a patient's pacemaker in the current flow towards the return electrode. The potential harm is quite serious, but there doesn't seem to be anything obvious we could do to make the system inherently safe. In this case, we chose to reduce the probability of this situation from occurring by relying on the trained clinical professionals by training them for using this device and putting warning signs in the user manuals and on the device to alert the users. But of course, this will only work if the user pays attention. Just like this course only works if you pay attention too, you and the lecturer. You should both pay attention. You too, reader, look at the camera. No, don't read it out loud, that was a scripting cue. Now look at the... So, I hope you now have a good impression of the 3 types of risk control measures. And remember, inherent safety first.